State and prove the Liouville theorem. Now statement: let fz be an integral function satisfying the inequality modulus of f of z is less than equal to m for all values of z, where m is a positive constant, then f of z is constant. Now proof: let z1 and z2 be any two points in a z plane. Suppose that C is a circle of radius r having center at z1 and enclosing point z2. This is point z1 and there is a circle enclosing z2. z1 is this at the center of this circle. From Cauchy's integral formula, we have f of z2 minus f of z1 is equal to 1 upon 2 pi integral f of z upon z minus z2 dz minus 1 upon 2 pi iota integral c f of z upon z minus z1 dz, which is equal to 1 upon 2 pi square bracket integral c bracket starts z minus z1 plus minus z plus z2 bracket close upon bracket starts z minus z2 bracket close bracket starts z minus z2 bracket close f of z dz square bracket close. So which is equal to 1 upon 2 pi integral c z2 minus z1 upon bracket starts z minus z2 bracket close bracket starts z minus z1 bracket close f of z dz, which is further equal to z2 minus z1 upon 2 pi iota integral c f of z dz upon z2 minus z2 and z minus z1 into z minus z1. Now let us choose r so large that modulus of z2 minus z1 is less than r upon 2. Since modulus of z minus z1 is equal to r, we have modulus of z minus z2 is equal to modulus starts bracket starts z minus z1 plus z1 minus z2 bracket close modulus close is equal to modulus starts bracket starts z minus z1 bracket close minus bracket starts z2 minus z1 bracket close modulus close is greater than equal to modulus of z minus z1 minus modulus of z2 minus z1, that is greater than r minus r upon 2, and which is greater than equal to r upon 2. Also we know that f of z is less than equal to m given, so therefore modulus of f of z2 minus f of z1 is equal to modulus of z2 minus z1 upon 2 pi iota integral c f of z upon z minus z1 into z minus z2 dz modulus close. So which is less than equal to modulus of z2 minus z1 upon 2 pi integral modulus of f of z and modulus of dz upon modulus of z minus z1 into modulus of z minus z2. So which is less than equal to modulus of z minus z2 minus z1 upon 2 pi integral in place of f of z m into modulus of dz, and z modulus of z minus z1 is r, and z minus z2 is r upon 2, z minus z2 is r upon 2. So then that is less than equal to m z2 minus z1 upon 2 pi this is r square upon 2 integral dz. Now dz is equal to 2 pi r integral of dz modulus dz is 2 pi r, so which is equal to m modulus of dz z2 minus z1 upon pi r square 2 pi r, that is equal to 2m z2 minus z modulus of z2 minus z1 upon r, letting r tends to infinity. So we see that modulus of f of z2 minus f of z1 is equal to 0, which implies f of z2 minus f of z1 is 0, which implies f of z2 is equal to f of z1, which shows that f of z is a constant.